and which is a fundamental paper where we actually applies his theory of heat to the temperature of the terrestrial globe, and he studies the role of the rays of the sun in particular, and he indicates the regulatory role of sea currents and winds on terrestrial temperature, and he also imagines the effects of human industry. So it's truly founding text on climatology. So and it's not only a great Fourier year, but it's also a great Fourier week, because this photograph of the Fourier of the buste of Fourier will be inaugurated next Friday in Paris in the Père Lachaise cemetery. So you are all welcome to join us next Friday afternoon if you are in Paris by chance. Okay, so let me now directly start with okay, what's happening? Okay, yes. So I wanted to raise the problem of how to detect chirps and oscillatory singularities in signals. So first, I would like to give you some kind of visual idea of what is a chirp if you have not met one. The first one is a little bit hidden. It's an ultrasound emitted by a bat. And actually, you really need, you don't see much on the signal here. You really need a local Fourier analysis to realize that there is something happening here. The second one is more clear. It's a theoretical gravitational wave. So it's not actually the gravitational wave that was detected, but it's the closest one, which was theoretically calculated. And what you can see on this picture, also on the top left, is a signal which is modulated in time and frequency. You see the size of the magnitude of the signal increases and then decreases, and the frequency also changes. And here are other two occurrences of things a little bit similar. The one on the bottom right is I will come back to it. It's called Riemann's non-differentiable function, because it was proposed by Riemann as a possible example of a continuous nowhere differentiable function. You can actually see on the little zoom that it is actually differentiable at some points, and at these points of differentiability, you have also a similar phenomenon of frequency, which is increasing until up to the point of singularities. And the one on the bottom right is our recordings of EEGs at different locations in the brain. And if you look, for instance, at the green recording in the middle, you see also a similar phenomenon. Frequency, frequency which is increasing until fast increasing at some points. So this is loosely speaking so what we will call chirp or oscillating singularities. So this is an approximate formula for this theoretical gravitational wave. And a possible definition of a chirp is a function which is the f of t, which is the product of an amplitude a of t, which changes with location, and then a frequency, which also depends on frequency, which also depends on time. And the two conditions at the bottom mean that basically the amplitude does not change much from one oscillation to the next one, and the frequency also does not change much from one oscillation to the next one. Okay, so this is an okay definition for many kinds of data. Actually, we won't be so happy with it because it requires a lot of smoothness. You know, you need to go up to two derivatives, and you want to also to to use this notion in situation where there is no differentiability. And so these kinds of data are called AM/FM signals, amplitude modulated, frequency modulated signals. Okay, so for instance, if I come back to Riemann's function, and I'll explain a little bit later why we're particularly interested in that, and this is a zoom around this the chirp, you can see on the oscillation of the function. So what would be the function phi is that actually it's not a smooth function. It's a rough function, which actually is not differentiable. So clearly this kind of functions cannot fit into the previous setting I mentioned. So we would like to have a definition which encapsulates this notion, but it's more robust to the lack, for instance, the lack of differentiability. Okay, so here's the problem that the function phi is not smooth. Let me just mention why we are interested in Riemann's function. Well, at the beginning, it was more like a nice mathematical functions, which has many interesting properties. But actually, recently, there have been really nice and unexpected connections with turbulence. And essentially, so this is a picture of the real versus imaginary part of the complex Riemann's function, and it has been given an interpretation in terms of fluid mechanics as a trajectory of the corners of a polygonal vortex filament. And so these functions meets an important requirement in turbulence, which has been present for a long time, to understand if there are oscillating singularities or chirps like that in turbulence data. And this theoretical finding tends to prove that indeed it can be the case, and it rises, I mean, it increases the importance of being able to detect such phenomena of strong oscillations near singularities in real life data, for instance, in turbulence data. Okay, so let me come back again to Riemann's function, and actually it can be shown that it has a form which is a little bit like the A of t cosine phi of t that I was mentioning, except that if you look in the second term, the oscillatory part, so the r tilde of 1 over x plus x, r tilde of 1 over x, and so on, is a rough function. It's not a smooth function. And this is what we were actually seeing on the picture, but you can actually prove it. It's essentially Riemann's function. So it has a kind of form which is a little bit like this AM/FM signal, but not using these regularized assumptions. So how can one, I come back again to this problem, how can one characterize such behavior without using this modeling, which requires some differentiability? And this can be done by inspecting the pointwise regularity of the functions and of other functions which are associated with it. So let me recall the notion of the most classical notion of pointwise regularity, which is Hölder pointwise regularity. So a function belongs to C alpha of x naught if the function minus its Taylor expansion is bounded by x minus x naught to the alpha, and basically the Hölder exponent at the point x naught is the best possible alpha that you can pick in this definition. Okay, so this is the most simple, the type of pointwise singularity that you can imagine, a cusp, like x minus x naught to the h. And if h is not an integer, then the older exponent at x naught will be exactly h. But you can have other functions which will have the same order exponent and which really won't look like, and this is typically what, again, we refer to as a chirp, where you multiply the cusp, x minus x naught to the h, by your very fast oscillating function like sine 1 over x, and actually you can pick sine 1 over x to a certain power beta. And in that case, h will be the older exponent, as expected, and beta, we want to know how we can characterize the oscillations near the singularity, and they will be characterized in that case by the value of beta, which we will refer to as a oscillating singularity exponent. Okay, so how can we draw a difference between these two? Let me come back. These two functions, which look really different but have the same pointwise regularity. And a way to do it, a simple way to do it, is to estimate the regularity of the primitive of the function. So of course, if you take a primitive of x minus x naught to the h, you will get something like x minus x naught to the h plus 1. So the older exponent is increased by 1 under one integration. Whereas if you have an oscillating singularity, it's a very simple exercise of integration by part, which shows that actually the older exponent is increased by not by 1, but by beta plus 1. So you can see the difference, and actually you can even determine the exponent beta just by comparing how much the pointwise regularity is increased under taking a primitive. Okay, so we would like to basically to transform this very stupid remark into something that can be efficient and can be used in signal processing. And for that, I will have to use a wavelet characterization of pointwise regularity, which many of you know, but I will recall that briefly. So we use, so I will present everything in one variable, and of course, all what I said extends to several variables. So we start with an orthonormal wavelet basis, classical orthonormal wavelet basis. And what I will, okay, the important point is the notations I will use. I will index wavelet coefficients by dyadic intervals. So the lambda is k over 2 to the j, k plus 1 over 2 to the j. So basically, if I was using the R system, the lambda would be just the support of the wavelet. So if you use the Dobouchi's wavelet, it's the support of the wavelet is a little bit larger, but basically lambda, if you think of lambda as the support of the wavelet, you don't do a big mistake, okay? And I use the notation 3 lambda for lambda, so which is here the middle interval on the top, and it's two closest neighbors. And the result I will use is a way to characterize pointwise regularity in terms of not exactly wavelet coefficients, but a quantity that we refer to as wavelet leaders, which are local suprema of wavelet coefficients. So basically, the idea is that you increase a little bit the size of the interval by taking the two closest neighbors, and then you take all intervals which are included inside this increased dyadic interval. Okay, and you take a supremum of all wavelet coefficients inside this box, so which is theoretically taken on an infinite number of wavelets, but in practice you have to cut somewhere. And the result I will use is that if you have a little bit of uniform regularity, then you can derive the pointwise order exponent as basically a log-log plot regression of these wavelet leaders versus the scale of the scale of the wavelet. Okay, so that means that that formula at the bottom means that if you look at the wavelet leaders localized above a point x naught, the order of magnitude of their size is 2 to the minus hj, where h is the pointwise exponent. Okay, I will use another notion also of pointwise regularity, and we will see a little bit why I need to get some extra room and use alternative notions, which was introduced by Calderon and Zygmunt in the 1960s, because it generalizes pointwise order regularity for functions which are not necessarily locally bounded. So the idea is very simple. If you rewrite the pointwise order regularity condition as a little L infinity norm, so you take a little L infinity norm of f minus its Taylor expansion on a ball of radius RR, and you require this L infinity, local L infinity norm to be bounded by R to the alpha. So this is clearly equivalent to the definition at the top. But if it's rewritten like that, you can say, okay, this is good if f is locally bounded, then, but if f just belongs to LP, instead of taking a local L infinity norm, I can take a local LP norm. And this is exactly the definition that Calderon and Zygmunt gave. You take an LP norm, a local LP norm on a small ball of radius epsilon, and you want it to decay. You properly renormalize it and want it to decay like R to the alpha. Okay, and you define a P exponent, which is just like the order exponent, except that you are using this this definition. Okay, so actually Calderon and Zygmunt introduced it because it had better properties in terms of in order to when you study different pseudo-differential operators, pointwise order regularity does not behave well, but this notion behaves better. Actually, another reason is that, as I said, it allows to give a notion of pointwise regularity for data which are not locally bounded, and it allows for regularity exponent to take negative values. Okay, and in that case, you also have a characterization of pointwise regularity for this notion in terms of something which is a little bit different from wavelet leaders, which we call P leaders, and the difference basically it's the same. We consider the same little box around the dyadic interval lambda, but instead of taking a local little L infinity norm, we took a local little LP norm of wavelet coefficient, which with a good normalization. And then you have the same formula as above for the P exponent, which tells you that you can estimate this pointwise regularity by a local log-log plot regression of these P leaders against the scale again of the wavelets. Okay. So I will introduce a notion that I won't use very much, except that I will extract some information about it. So the idea is now we have a tool, we have a collection of pointwise exponents, the order exponent and all these P exponents. Actually, the order exponents corresponds to P equal plus infinity. And as I said before, when I gave the motivations to estimate chirps, we want to consider also regularity of primitives of the function. Okay, so actually we won't do just primitives, but also fractional integrals. And basically the maximal pointwise information you can dream of is given by what we call the fractional exponent, which basically gives you at a given point x naught all p exponent, Euler exponent, and all p exponent, not only of f, but also of all its fractional derivatives or fractional integrals whenever they are defined. Okay, so this is not exactly that. I subtract the s, the order of integration. So the point of subtracting s is that I want something to be constant for cusp. So I take out the amount of integration, and actually we won't look at that as it's more convenient to look at that as a function of 1 over p and not of p. So what we really call the fractional exponent is a 1 over q exponent of a fractional integral of order s of f minus s. Okay, so this is a little bit complicated. It's some simpler version have been explored by Jacques Lévy-Vels, Stéphane Seret, Paul Balança, and Eric Herbin, and in particular, they were determined for many functions or stochastic processes. Okay, so actually this is too much. I mean, we don't want to determine for, I mean, we don't expect to find if we have a signal, all this full two variable function, which is defined at every point. I mean, it's really too much. So what we want to do is to extract some information, some parameters from this too rich information, which can be relevant and will tell us that indeed we have some behaviors like the chirps I was mentioning, and also other behaviors I will mention. Okay, so how can we do that? Let me just come back again to this simple function. So first, the cusp, actually, so I mean, everything was made so that this fractional exponent is actually constant and equal to h. So it does not change if you compute p exponents of cusps, it does not change. It does not change with p. And if you take a primitive, it increases just by the order of primitive. So if you subtract the order of integration, you get something constant. This is kind of trivial. What is nice is that the fact that this function is constant, h of sub f and x naught, is equivalent to a condition which seems much weaker, which is just the fact that two derivatives of this function computed at a point vanish. Okay, so this is just a consequence of some equations which are satisfied by this function. I don't want to go too much into details, but it tells us that this gives the idea that we could use the fact that these two this derivative vanishes as saying that, well, for more complicated functions, but that will look like cusps, we'll have the same the same behavior. So what we call a canonical pointwise singularity is a function for which this derivative just vanishes. And otherwise, we said that the function has an oscillating singularity. And that essentially means that when you take a primitive, the Euler regularity, for instance, will increase by more than 1. And in that case, so if this derivative does not vanish, the value of this derivative we call the oscillation exponent. And if we come back to the chirps that I showed, it's actually the beta that I showed. So now let's consider something a little bit different from the chirps, which is what we can call syncombs. Basically, the idea is that it's other singularities for which when you take a primitive, the Euler regularity will be increased by more than 1, but for a different reason than for chirps. For chirps, basically, we had this sine 1/x, which was oscillating very strongly. So when you are taking a primitive, these oscillations were canceling, and you have a strong increase of regularity. And here, it's not a consequence of the oscillation, but it's a consequence of the fact that, well, it doesn't show very well on the picture, but basically, the function essentially vanishes, except on very thin lines which look like a comb, and so that when you take a primitive, you have something much smoother than you would expect. So it's because of it's not because of cancellations of signs, but it's because of the sparsity of the little teeth of the comb that you see. Okay, and if you compute, this is not a complicated computation. If you compute this is a fractional exponent for this function, you find that basically these two derivatives are equal, and we can define the lacunarity exponent, which basically tells you how lacunary the singularity here is near the singularity by this derivative of the fractional exponent. Okay, so this is one possible lacunarity is one possible cause of having an oscillating singularity. Okay, and so the other cause is I already talked about it. What happened with these chirps, and for these chirps you can compute the again, it's an easy computation, the fractional exponent. And basically you can see that this chirp satisfies the fact that the exponent does not depend on the p exponent, on the value of p. So when you take a derivative of the fractional exponent as a function of q, you have 0 exactly, and which was not the case before, which was not the case for lacunary combs. And okay, you can show that actually just the fact that this derivative vanishes implies that all p exponents coincide, and we can define the cancellation exponent, which will exactly be the exponent beta here as the difference between these two derivatives. Okay, so basically the idea is that the oscillation exponent, let me say again, when you take a primitive, you look how much the regularity is increased if you take a primitive, subtracting 1. You can split it into two different behaviors. One which is caused by the lacunarity of the singularity, and another one by the cancellation. Okay, so you can imagine that you have basically a superposition of a chirp and a lacunary singularity, and so this gives basically these two exponents together with, of course, the elder exponent. So these three exponents give you the relevant information and encapsulate the relevant information concerning the nature of pointwise singularities. Okay, so for instance, if I come back to Riemann's function, you can show that it has no lacunary singularity. You have these very strong oscillations which take place at the differentiability points. So you have balanced singularities, just like the chirps, with exponent 1. And okay, and otherwise, all the other singularities are canonical singularities. Okay, so a different situation is made by random wavelet series, which are a nice model stochastic processes, the regularity of which changes from point to point. And so the definition of the model is that at each scale, basically you pick at random. So at each scale, you have essentially 2 to the j locations for wavelet coefficients, and you pick at random 2 to the eta j locations where eta is between 0 and 1. So you pick at random very few locations, and you take wavelet coefficients 2 to the minus alpha j. So it depends on 2 parameters: the lacunarity parameter eta and the regularity parameter alpha. And this is on the bottom. This is the sample path of such a process. And because of the lacunarity, these stochastic processes will present actually lacunary singularities. And you have a very small set of canonical singularities of Hausdorff dimension eta. And all the other points are lacunary singularities. And okay, and you can compute the full at every point the fractional exponent. And so basically, this example shows you that okay, lacunary singularities are produced, for instance, as a consequence of sparsity. I mean, you have a sparse wavelet series here. And randomness. You don't organize the location, you don't relate the location of the large wavelet coefficient, you pick them at random. And these two, sparsity and randomness, imply lacunary singularities. Okay, let me mention another important, actually much more important collection of stochastic processes, which are Levy processes. So the definition is that they are stochastic processes with independent and stationary increments. And so this is very interesting because not everything is known on these for these processes. There has been a breakthroughs a few years ago by Paul Balança, who proves that for some Levy processes have sample paths which have only canonical singularities, and other have display oscillating singularities. And actually, Paul Balança gave some information about the size of points where you have both behaviors. But as I said, there are mainly open problems concerning that. We don't know. I mean, Paul found a few examples of categories of Levy processes which have either only canonical singularities or lacunary singularities, but we don't have the full picture. We are very far from having the full picture, and also he gave some estimation about the size of the set of points where this lacunarity exponents show up. But okay, so for instance, we don't know if balanced singularities can be met in sample paths of Levy processes. I would be very surprised by that, but I cannot exclude it because, as you saw in the case of a chirp, having a balanced singularity means that you have very precise sign compensations, which you really don't expect to meet in a standard random process. But this is just my feeling, and I have no proof of that. And this raises, I mean, this very loose argument that I just gave you raises the problem of knowing if there are some classical stochastic processes which display balanced singularities or not. So I would tend to think that the answer is no, but having a general theorem saying that large classes of stochastic processes cannot display balanced singularity would be very nice. And the next question on which we will focus during the second half of this talk is, okay, if you have a stochastic sample path of a stochastic process, or or some data which you have recorded, can you put in evidence the existence of lacunar singularities or balanced singularities in the data in a numerically efficient way? Okay, so it's for such processes, basically the singularities are each type of singularities are everywhere dense. So you don't expect a method that would really focus at a point and determine at this point what are the exponents. You don't expect such a method to be successful because everything is dense everywhere. Basically, that's the idea. And so all classification methods based on the determination, on the direct determination of the exponent prove numerically unfeasible. And that's why in such situation, one uses the ideas behind multifactorial analysis, which I will now quickly recall. They were introduced by Giorgio Parisi and Uriel Frisch in the 1980s. And they are less, I would say, less demanding than determining at every point a pointwise regularity. But the idea is just to derive some information about the sets, the size of the set of points, where pointwise regularity exponent takes a given value. So you don't want to know what is the regularity everywhere, but does the exponent, for instance, 1/2 shows up on a big set, or is it truly exceptional? Something like that. Okay, and I will use I will use some extension, actually a recent extension of multifactorial analysis, which we call multivariate multifactorial analysis, and I will just consider the bivariate case. So we'll consider two signals, two data, x1 and x2, and we have two regularity exponents associated with each signal, okay? And we assume that we are in the situation that I showed for the order of the p exponent, that each exponent can be derived locally by a log-log plot regression of some quantities, which can be wavelet leaders or wavelet p leaders or other quantities that you take your favorite local multi-resolution quantity. And the rule of the game is to derive some information of this set E of H1, H2, which is a set of points where the first exponent takes a given value, capital H1, and the second exponent takes another value, capital H2. Okay, and what we call the joint multifactorial spectrum is just the Hausdorff dimension of this set of points. Okay, so it's mathematically, it means that you can see the definition of A of H1 and H2. It's just the intersection of two sets, the set of points where H1 takes the value H1, and the set of points where H2 takes the value H2. So mathematically, it's a quite difficult problem, which is in the situation where such sets are fractal sets, you want to determine the Hausdorff dimension of an intersection of two fractal sets. Okay, so now how can we estimate it numerically? And this is the idea behind this is the idea that Uriel Frisch and Giorgio Parisi introduced, which I rewrite in a bivariate setting, but it's really the same idea. You consider quantities which are just averages. The 2 to the minus j just means that you take an average of the first multi-resolution quantity to a p times the second multi-resolution quantity to a q. Okay, and then you make a log-log plot regression. You see how this S sub p of q and j, what is its size, its order of magnitude when 2 to the minus j goes down to 0, and this defines the bivariate scaling function. And the bivariate Legendre spectrum is just a Legendre transform in two variables of this scaling function. Okay, and we've said that we expect that this bivariate Legendre spectrum will give an estimation of the bivariate multifactorial spectrum D of H1, H2. So let me give you a rough idea, which is of the argument that leads to this formula. So I just recall that A of H1, H2 is a set of points where the first exponent takes the value H1 and the second exponent takes the value H2. So, and D of H1, H2 is its fractal dimension. And so we consider these structure functions, okay? And so the idea is to estimate contribution of the Dadi cubes of generation J of width 2 to the minus J to this quantity, to this structure functions, okay? And we estimate the contribution of the points where the first exponent takes the value H1 and the second takes the value H2. So in that case, we know that D1 sub lambda is of the order of magnitude of 2 to the minus H1J, and D2 sub lambda is of the order of magnitude of 2 to the minus H2J. So the contribution of this point to the structure function is the following. So there are about, because of the definition of fractal dimension, there are about 2 to the d of H1, H2J cubes of this type. You need about that number to cover the set. And so the contribution is 2 to the minus dj, which is just the normalization in front. And the sum contains 2 to the d of H1, H2J Dadi cubes. And for such a Dadi cube, D1 lambda takes the value 2 to the minus H1J, and D2 lambda takes the value 2 to the minus H2J. So it's just an easy computation to estimate this contribution. Okay, and now when J goes to plus infinity, the idea is that basically for each couple H1, H2, you have this exponentially decaying term, okay? And when J goes to plus infinity, it's the one corresponding to the smallest exponent that will bring the largest contribution. So the order of magnitude of the global sum on all exponent will be just given by the infimum on all H equals H1, H2 of this quantity. Okay, let me come back. Okay, so actually this is where the Legendre transform shows up, except that on this formula it goes the wrong way. We can compute eta and we want to find D, so we have to go the other way. And assuming that eta and D are concave, you can invert the Legendre transform by a Legendre transform its own inverse, and so you can recover D of H1, H2 as a Legendre transform of the scaling function. Okay, so this is a nice formula. This is basically the physics argument rewritten in a bivariate setting that Frisch and Parisi gave. And it has, okay. In the univariate case, okay, so it's not true in general. Okay, this, let me come back. This formula at the bottom does not hold in general. If we are just one signal, so we are just one P and no Q, that will be the univariate case. One can show that actually the Legendre spectrum yields an upper bound for the multivariate multifactorial spectrum. So you could hope for that in the bivariate case, But actually, the bad news is that the result fails in general in the multivariate case. So this is, I mean, this is a real problem. I mean, that does not need to be a connection between what we can compute, the Legendre spectrum, and what we want to have some information about, the multivariate spectrum. But the good news is that there are several subcases. So I don't want to go into details here. If basically if the multi-resolution quantities have satisfy some compatibility conditions, you can the same upper bound holds in two variable or in more variables. Okay, so actually the good news is that it is the case, for instance, if you take for the two exponents, the older exponent of a function and the older exponent of its primitive or its fractional primitive of any order. Okay, so that means that the Legendre spectrum in that case will give information about the set of points where the older exponent takes a value and its primitive takes another value. So it will give you an information about the existence, the possible existence or non-existence of chirps or oscillating singularities. And this is really where I wanted to go to. So before going into that, let me just show you a few numerical examples. So first, a trivial case, somehow, if we make a bivariate analysis of a function and itself, of course, the spectrum is supported by the main diagonal, because when at the point where the first function takes the value h1, the second function also takes the value h1 by definition. So we have a spectrum supported by the main diagonal, and this is exactly what is computed numerically. Okay, so this is not very interesting, but this is just to show you. Another case is if we analyze two independent stochastic processes. So in that case, and we assume that they are stationary and essentially that the wavelet leaders are independent, okay, or have just short range correlation. So in that case, you can interpret this average as an expectation, and you have an expectation of a product of two quantities which are independent, and the decorrelation just tells you that it's the expectation of the product is the product of the expectation. So what does that mean on the Legendre transform? That means that the Legendre spectrum of the couple of these two stochastic processes are just the sums of the Legendre spectrum minus the d, which is the space dimension. Okay, so this exactly means if you remember that we want to interpret these Legendre spectrums in terms of Hausdorff dimension, it just means that the codimension, recall that we are computing dimensions of intersections of sets, intersection of the sets where the first exponent takes a given value and the second exponent takes another value. And this just tells you that the Legendre spectrum follows the codimension formula for intersection. I mean, the fact that the classical case that the dimension of an intersection, the codimensions add up for intersections. For instance, if you, in the smooth case, in dimension 3, generically, if you intersect a plane, two planes, you will get a straight line. So that just means that the codimensions add up. Okay, and there are some mathematical theorems made by Mattila and his collaborators, which shows up that from large classes of fractals, this happens. Unfortunately, there are also many counterexamples for these types of fractal sets. So this is what the what the Legendre spectrum will give you, but that really does not prove that will be the case for the other dimensions of the singularities. And let me finish with some real life data in which we studied data which were recorded on the marathon runners. And this is the bivariate analysis here of the heartbeat, which is known to be a multifactorial quantity, and the speed of the marathon runner. And you see something which is not really localized not really supported. So this is the structure function on the left, and on the right are the Legendre transform. So here you see that it's not really supported on a line. So that means that there is a kind of there is not a perfect dependence between the singularities of heartbeat and speed. But if you look at speed versus cadence of the steps, you see a much thinner support, which means that you have really something like close to a perfect correlation. And now let me come back to my initial motivation. And here we analyze the heartbeat frequency again for marathon runners, and it's primitive. Okay, so if it's supported on a line, it will mean, because of the upper bound, it will mean exactly that there are no oscillating singularities, and which is really the case. I mean, in the middle you see the spectrum. On the left and right are the projections, so the one variable spectrums, and you see a perfect correlation, meaning proving that there are no oscillating singularities in the data. And this is again the same analysis for the cadence of the marathon runners. And again, we have something which is very close to be supported on a line, meaning again that there are no oscillating singularities. And again, the same for the acceleration of the runners. Okay, so that were first experiments for on this data of marathon runners. And I just to finish, I want to mention that we have an ongoing program with Patrice Abri and Françoise Argoul to analyze. This is really the motivation I gave at the very beginning to analyze turbulence data, and determining if there are or not oscillating singularities in turbulence data would be important. First, for our comprehension of the nature of turbulence, but also this would validate or invalidate turbulence models which have been proposed by physicists, and some of which includes oscillating singularities and some of which don't. And I mentioned at the very beginning brain data, and I showed this EEG which seemed to display oscillating singularities. And we also have some collaborations with Jean-Marc Lina and David Lockman to know if it is indeed the case. Okay, thank you very much for your attention.